So hello, everyone. My name is Samuel Sanchez Lopez. I'm a third-year PhD student at Lancaster University. And yeah, today I'll tell you about quintessential inflation in Palatini modified gravity. This talk is largely based in these two papers, the first of which was published last year, and the second of which was actually published today. So very, very quickly, most of the history of the universe is well understood, at least in general terms, except for the very early universe. We don't know how the universe came into existence, and the present cosmic time. There's a new substance called dark energy. We don't know what it is, but it's making the universe accelerate again. So what is inflation? Inflation was proposed in the 80s to solve the horizon and flatness problems. But its huge success lies in the fact that it provides a mechanism for the generation of primordial perturbations that source basically all structure in the universe. So, for example, the temperature anisotropies in the CMB. There's a plethora of different models, but even like the simplest ones that you can write, like this action here, this is just Einstein-Hilbert gravity, a canonical kinetic term, and a potential, already give pretty good predictions. The equation of motion for the inflaton in this case can be analytically solved. In the slow roll approximation, you just neglect the second derivative, and at a classical level, you also neglect the spatial variations, and the observables can be expressed in terms of the so-called slow roll parameters, eta and epsilon, which again are just functions, simple functions of the potential. Here I'm showing the Planck data. They are these blobs in superposition with the predictions of some models, and I would like to focus in specifically two of them: R squared inflation, which corresponds to this green line here at the bottom, and alpha attractors, which is this yellow box. It's important to know that for alpha attractors, you can make the tension to scalar ratio arbitrarily small just by changing alpha. So both models lie at the sweet spot of the Planck data, and what they have in common is that the potential features a plateau. So in this sense, potentials with the plateau are observationally favored, and we will come back to this later. And what about dark energy? In the recent past, it has been measured that about 70% of the universe is made up by this mysterious substance. We call it dark energy, but nobody really knows what it is. And it's making the universe accelerate again. Traditionally, it's explained by adding a cosmological constant to the Einstein equations, but as it is well known, this requires an extreme amount of fine-tuning. And there have been many attempts to solve this. An important one is perhaps quintessence, which models dark energy as a scalar field, and many times just with a simple action, just as this one that I showed before for inflation. However, the problem of fine-tuning is just hitting away in the initial conditions of the field, which still need to be explained. And this is where quintessential inflation comes into play. Quintessential inflation basically identifies the inflaton and the quintessence fields. And perhaps the biggest advantage of this approach is the fact that the initial conditions for quintessence are fixed by the inflationary attractor. This is, I think this is very nice. And here I'm showing the original potential proposed by Peebles and Belenking, which is now observationally discarded, but it serves the purpose to show that all models of quintessential inflation feature this new cosmological era in the expansion, like in the history of the expansion of the universe, called kination. When the energy density of the universe, it's still dominated by that of the inflaton, which is in turn kinetically dominated. And the existence of this kination era implies that the number of E-folds of inflation is increased from the usual 50 to 60 to 60 to 70, or roughly, or 75, 70 something. Okay, so now let's talk about what we actually did in the paper. We considered simple exponential potential, which is well known to be observationally discarded both for inflation and for dark energy. And we rescue it. We make it work as a quintessential inflation model just by considering the following setup in modified gravity. We add an R-squared term, and we add no minimal coupling between gravity and the field. Both of these terms are expected by renormalization considerations in QFT in curved spacetime. So in a sense, it's a natural thing to consider. And we work in the Palatini formalism. For those who don't know what the Palatini formalism is, it basically just means to consider the connection and the metric to be independent fields, as opposed to the metric formalism, which is the usual formalism that we learn in our bachelor's, where the connection is just the Levi-Civita connection of the metric. So here I'm showing the action in the Jordan frame, and by an appropriate conformal transformation, we can express it in the Einstein frame, where gravity is just the Einstein-Hilbert gravity. And the payoff for doing this is getting a modified kinetic term and a modified potential, plus some extra higher order kinetical terms, which when the field is slow rolling, they are just negligible. And why is this nice? Because if the potential is a monotonically increasing function with the field, as is the case for very large negative values, this term becomes much larger than this other term in the denominator. So both potentials cancel out, and the overall potential is just a constant. And this is what gives rise to the plateau that I said before in the beginning of my talk is observationally favored. So this is the reason why inflation works now. Also, as a comment, I don't really have time to go into this. We also considered a logarithmic running for the no-minimal coupling between the field and gravity. So here I'm showing how the potential changes after the conformal transformation. On the left-hand side, this is just the exponential potential in the Jordan frame. And after the conformal transformation, we see how the plateau appears. And yeah, here in the middle, we will have kination. And then at the end, it's the dark energy era. Okay, so we also solved the full equations of motion in the Jordan frame numerically. We did a parameter scan of the theory, and that's what I'm showing here in the kappa psi star plane. Kappa, remember, is the strength of the exponential, and psi star is basically the no-minimal coupling. And these are our results. In blue are all the points that give a correct value for the scalar spectral index. And in orange are all the points that give a correct value for the scalar spectral index, for the tensor to scalar ratio, and a correct range for the number of e-folds. And I would like to show you one specific point in this valid parameter space, just to show that we don't get any crazy numbers or something. It's all reasonable. And for this point, yeah, the predictions for inflation are perfect for 72 e-folds. We also solved, so we solved the whole thing, like from inflation until the present time as well. And here I'm showing the barotropic parameter of the universe in blue and of the field in orange, as a function of the logarithm of A. So today corresponds to the origin. The universe in our model is basically made up by two components. One is the field, and the other one is a background fluid, perfect fluid, that can be either radiation, giving rise to the radiation-dominated era, or pressureless dust, giving rise to the matter-dominated era. And we're interested in what happens today for dark energy. So for that, we consider the CPL parameterization, which is just basically a Taylor expansion of the barotropic parameter of the field. With WA, it's just the running, is basically the derivative of the barotropic parameter with respect to the scale factor. And why is this important? Is because this is going to be measured in the near future by some experiments like Euclid. And if this number is measured to be non-zero, that means that the dark energy cannot be a cosmological constant, because of course, a derivative of a constant is zero. So these are the Planck bounds on these two parameters. And these are our results, which are imperfect agreement again with observation. So just as a summary, quintessential inflation is an economical way of modeling the history of the universe. The initial conditions of quintessence are fixed by the inflationary attractor. Adding a minimal coupling term and an R-squared term in the Palatini formalism rescues the exponential potential, which is otherwise discarded by observation. And solving the equations of motion in the Jordan frame allows us to obtain specific predictions for the running of the barotropic parameter of the field, and this will be tested in the near future. Thank you for your attention.
Cool. Okay, thank you very much, Samuel. Do we have any questions? Oh, one straight away. So can you trust the Lagrangian post-transformation during a kinetic-dominated phase? That's corrections to the kinetic energy becoming important.
Right. Yeah. We solved the whole thing numerically, and we saw, well, I don't have the graph here. Maybe I can show the paper. Well, in any case, numerically, you can see that these terms are also negligible during the kinetic dominated era. You can see that in the paper. We solved that numerically, basically.